Okay guys, in this video we just want to get into this chapter on trapezoids, isosceles, trapezoids, and kites. So we're going to start out with the trapezoid. Okay, the trapezoid is, maybe some of you guys have a decent idea about this, but a trapezoid is a quadrilateral with two parallel sides. Okay, so of course we have some drawings over here of quadrilaterals, but basically quadrilaterals are going to have two congruent sides. Okay, something like this. All right, the congruent side, or sorry, not two congruent sides, two parallel sides. The two parallel sides are called the bases. Okay, so this is a base, this is a base, and then these are called the legs. Okay, so these are the legs. So trapezoids have legs and bases, and so especially if you guys already know the area of the area of a trapezoid, you might already know some of these things because we use the language of bases. So this is what a trapezoid is. Let's look at this theorem first. We're gonna in our next video look at some special kinds of trapezoids, but this is just for any trapezoid. It's called the trapezoid mid-segment theorem. It says if EF is the mid-segment of trapezoid ABCD, then EF equals half of BC plus AD. So let me explain sort of what's happening here. Okay, so this is cutting the legs in half. Okay, so EF is E is the midpoint of AB, and F is the midpoint of CD. So EF is the mid-segment, right? What this is saying is that if you add these two together, BC plus AD, and multiply it by half, that's going to equal this distance. Now this becomes really important, again, if you know the area of a trapezoid, and we'll cover the area of a trapezoid much later in another unit. But you recognize this is probably very familiar to you, and again, we'll talk about that later. But that's where the area of a trapezoid comes from this theorem. So why is that true? Well, we know from this problem, we're given all this information, and I'm going to say that I constructed a line parallel to these other lines. So this is also going to be parallel. Okay. Now from here, I can draw a triangle. Okay. Let me label this G. Okay. So we know that triangle CGF is similar to triangle CAD. So CGF, CAD, those are similar because angle and angle. Okay, so by AA similarity, those are similar. Now, we also know that since CF is congruent to FD, then that means that GC is going to be congruent to AG. Okay. So with that, we know that again, we also know that triangle EGA is congruent to triangle BCA. So BCA, EGA, those are congruent. So you have this little triangle is congruent to the bigger triangle. This little triangle is congruent to this, or sorry, not congruent. They're proportional, similar, so they're proportional, similar to this bigger triangle. Okay, so we have that. Now this is sort of the setup of how we're going to actually use this. Now, EG, okay, we see here, let's call this section A. Let's call BC, let's value that at A, okay? Well, the scale factor, okay, so let me write this over here. The scale factor of triangle see, triangle AEG to ABC, triangle ABC equals 1 to 2, because this is 1, this is 2, so it is 1 to 2. So if that's 1 to 2, therefore EG equals 1/2 of BC. Okay, in other words, that equals half of A. Okay, so by the exact same argument, here let's call this point, or let's call this distance B. Okay, and by the same logic, okay, these two triangles are similar, so their sides are proportional, and so it's a ratio of 1 to 2. Therefore, okay, by the same logic, I won't write it all out, but also GF equals 1/2. GF equals 1/2 of AD, which equals half of B. So, using this, EG and GF, okay, so EG plus GF equals EF. Well, we know that EG, so that is equal to, again, 1/2 A plus B plus 1/2 B, okay, which we can write as 1/2 A plus B. Okay, and so this is sort of proved, basically that this line is equal to half of the sum of the bases. So you add this base, divide it by 2, and that's going to be the distance of that midsegment. Okay, so let's look at some problems. First, this green one is the easier of the two. It looks like we have, let's see here, we need some more information here. Okay, we need to know that these are, okay. We need to know that that's true, because if that's not true, then we can't use the midsegment theorem. So this is our given here. Okay, so we know that this the trapezoid midsegment theorem says that 10 is going to equal this midsegment is going to equal half of it looks like x plus 14. Okay, so maybe you can do this in your head algebraically. If we multiply both sides by 10, that's going to be 20. So 20 equals x plus 14, so x equals 6. Okay, so, and just to check, 6 plus 14 is 20, half of 20 is 10, so that makes sense. All right, moving on to this problem, slightly more difficult. It looks like, again, we know that using proportional triangles, so first of all, before we jump into this, we do have a trapezoid and we do have a midsegment here. Okay, so we have parallel lines, which makes it a trapezoid. We have this point is a midpoint, this point is a midpoint. So this is a trapezoid with a midsegment. Okay, so we can use the trapezoid midsegment theorem. And again, we know that the ratio of because these two triangles, this big triangle and this smaller triangle, because those are similar, their sides are proportional in the ratio of 1 to 2. So if this is 5, we know that x is going to equal, looks like 2.5. And by the same logic, y is going to equal twice, because this triangle and this triangle have a scale factor of 2 to 1. So if this is 4, this is going to be twice as big, so y is going to equal 8. Okay, in our next video, we're going to look at some special types of trapezoids, look at some more theorems, and then continue through our chapter. Thanks for watching.